Welcome. In the previous tutorials, we have analyzed a cantilever steel beam, while that beam was subjected to a concentrated load at the free end. Both of the analyses were conducted in Abacus. One of them, the method 1, involved a beam modeled as solid 3D, while the second method involved a beam modeled as a wire element with beam type cross section. The links for those two methods and videos are in the description. But for this tutorial, we will try to solve the same problem analytically. So this is the beam that we will use. The cross-section specifications, you can find them in the file, you can find them in the description. I will put the link there. And now we will use Matlab to try to solve the beam. And we can start writing some specs. So we know that the length of the beam is 2000 millimeters. And we know that the load that we want to apply is 30,000 newtons. All right. And then we also know that the Young's modulus for steel is 210,000 megapascals. Very well. Now, let's see right here. There is a file, and the link to this file will be also in the description, a PDF file that shows how to compute displacements for several types of loading and supports. And for this case, which is our case, cantilever beam concentrated load at the free end, we will want to compute the displacement at the free end, and we will also want to compute the stresses, or the maximum normal stresses. Okay, so we can see here that maximum displacement at the free end equals to PL squared, equals to PL power 3 divided by 3 EI. This formula actually comes from somewhere, and it's according to Bernoulli-Euler beam theory, but we will not get into details on beam theory because we will do that in another video where I will also explain where does the displacement formula come from. Okay, so now we can go to Matlab and we can write here the displacement equals to P multiplied by L, the length, power 3 divided by, and here we have 3 multiplied by E multiplied by I. And now the only unknown that we have here is I, the moment of inertia. And this will be in millimeter to the power 4. And do you know how to compute the moment of inertia in Autocad? Well, it's good if you know, but it's if you don't know, it's also good because you find out right now. You should draw the section with the specs in the page in the description, as I have done here, and make it an object, just like that. But I will show you how to do it. I will explode this one first. I will write explode, enter, and select objects. I will select this one and enter. And now you see I can click it, and it's made out of several elements. And now if I write region and enter, I just select everything and enter again. And now you see it's highlighted all together. So now it is a region. And now the command that I want to use is mass prop, enter, select objects. And now I select the object that I have created and enter. So we see here in a window, we see the coordinates of the centroid according to our coordinate system that was placed before somewhere, of course. We also see the moments of inertia, which are with respect to our system of coordinates, and the principal moments. And this is what we are interested in, the moment of inertia along the x-axis. Yes? And just to show you that we can move this axis around, I will draw a small line here, and I will move the axis from here. I will move it to the center of the beam. Okay. And I will just delete this line. And now I will apply again the mass prop command. Okay, so mass prop, select the region, okay, and now you see the coordinates of the centroid are 0 and 0. But if you don't want to bother, you don't have to worry about that, because you can just place the coordinates system in a point where you would like, and then find the coordinates of the centroid right here. And you see here the moments of inertia on x and y are equal to the moments of inertia on the principal directions. Here is equal to here, and this is what we will use. Not before telling you that I will show you in another video how to compute the moment of inertia and the coordinates of the centroid for any section analytically. But now we just copy this value for the moment of inertia on x, and we go back to Matlab and paste it here. Right. So now we have the moment of inertia, and we can compute the displacement at the free end. But we also want to compute a maximum normal stress, as we said in the beginning. So we know that the normal stress, we call it sigma xx, equals to m, the moment, bending moment, divided by I, moment of inertia, multiplied by y in general. So this is Navier formula, y. And if you want the maximum stress, y is h over 2. It doesn't matter if it's compression or tension. This is a symmetric cross-section on two axes. So on the top fiber, this will be the maximum tensile stress, and on the bottom fiber, this will be the maximum compressive stress. All right, so this will be maximum normal stress at the extreme fiber in the support. Very well. And the moment, the bending moment, is just simply P multiplied by L. All right. And this is maximum or bending moment at the support position. And then h, the height of the beam, is 200, and these are millimeters. And now you see at some places I used semicolon at the end of the line, and in some places I didn't. And I didn't use the semicolon here and here, and it's because I want to have these two results displayed in the command window after I run. So let's run it to see what happens. And we can see in the command window the results for the displacement. And the results for the displacement are 1.4 to 10 power 1.4 multiplied by 10 power 41 millimeters. Yes, and this is because here, instead of multiplied, we had before 30 to the power 1000, so that's quite big. So here, of course, it needs to be multiplied, and we run it again. And we have this value for this displacement, 20.6 millimeters, and the normal stress in the cross section in the support and the extreme fiber, 325 megapascals. And that was this tutorial. Thumbs up this video if you liked it, leave a comment, and subscribe for more content. This is Blood Ink. Have a good day.